Hi, I'm Ehud Cherishak. Back in 1980, Russell Baker, a well-known New York Times writer, wrote an op-ed piece called Terminal Education, where he pooh-poohed computers as being in dark rooms in the basements of buildings. You could never take them out under a tree and enjoy the fresh air and sunshine. This is me in 1983 showing Russell that you can take a computer and interact with it under a tree as long as the battery doesn't flake out on you. Little did I know that at the time that I would be able to read a whole book under a tree, Kindle. I'm sure Russell Baker never would have conceived of the power of what presentation software can do. So let me share with you some pieces that I think Russell would have liked. I call them short math stories with a surprise twist. So let me move on to the stories. What I offer is story ideas that would make learning more interesting, stories that inform what I call a Math 2.0 curriculum. It builds on students' curiosity so they notice and wonder. This is not pablum they get today in Math 1.0 curriculums. Here's the stories. Let's begin. Not quite yet. Buffon's needle experiment. Fermat's last theorem debunked. How accurate is Google? The weird number. Numbers you can't count on. Greenglobes and Desmos, and Guillermo's big score. Now let's begin. Story number one. First one is the Buffon's needle experiment. Now, what do you notice here, and how about wonder is what you're going to be concerned about as soon as I turn on the activity. And I want you to turn to a colleague and share for 20 seconds. If you're watching this alone, well, think about it and I'll come back to you in 20 seconds. Well, I'm back, and what do you notice? Well, you notice some lines falling on, well, they could be needles or they could be toothpicks falling on parallel lines. But how do needles falling on parallel lines produce something related to circles? Well, you might notice that there's a number that is showing up that was approximating pi. It's a little off now, but it definitely is headed towards pi. And that's what's so unique about this particular experiment, that it tells you what pi is. Let's take a look at why. When you drop a needle on parallel lines, there are two possible outcomes. In drop one, the needle or toothpick lands between two parallel lines. Notice that the perpendicular distance to the line from the center of the needle, AB, is greater than the perpendicular distance from the center of the needle to the edge of the needle, DC. In drop number two, the opposite is true. AB is less than DC. Only caveat here is that you need to find the length of DC using trigonometry, which is 0.5 of the sine of angle DBC. So now let's graph the results and see what happens. Okay, if you graph f of x equal 0.5 sine of theta, which is actually the perpendicular distance from the center of the needle to the line, and that's the graph of it. It turns out that all the hits will fall below the curve, y equals 0.5 sine of theta, when the distance dc is less than the on the graph, you will see a blue dot is above the curve. When AB is greater than DC, as in this case, the dot will be inside or below the function and in the graph area. As you drop more needles, you plot more points, and the area under the curve fills up. To actually determine the area under the curve containing all possible hits is found by using some calculus, that is, integrating 0.5 of times sine of theta from 0 to pi, and that all equals 1. The area of the entire rectangle is pi over 2. So the probability of a hit is 1 over pi divided by 2, or 2 over pi. That's approximately 64% of the time the needle will actually fall on a line. To calculate pi from the needle drops, simply take the number of drops and multiply it by 2, then divide by the number of hits. This gives you an approximation for pi. Pretty nifty, huh? George Reese does a nice job of explaining this random madness and its connection to pi. When I write up this activity, I'll include the detail about the trigonometry, the radians, and pi. That's coming up in the near future. So let me move on to story number 2, which is Fermat's last theorem. Anybody familiar with that? Well, what about it being debunked? Wouldn't that be interesting? We're all familiar with the Pythagorean theorem, a squared plus b squared equals c squared. The solutions to this are referred to as Pythagorean triples. For example, 3, 4, 5 is a true statement. 5, 11, and 12 is another true statement. There's more. But what about a to the third plus b to the third equals c to the third? Looks very similar to Pythagoras. Wouldn't there be a solution to this? Well, that's the interesting part. According to Fermat's last theorem, Fermat states that no 3 positive integers, a, b, and c, can satisfy the equation a to the nth plus b to the nth equals c to the nth for any integer value of n greater than 2. This theorem was first conjectured by Pierre de Fermat in 1637, famously in the margin of a copy of Arithmetica, his book, where he claimed he had a proof. I have discovered a truly remarkable proof of this theorem, which this margin is too small to contain. No successful proof was published until 1995, despite the efforts of countless mathematicians during the 358 intervening years. Did Fermat really have a proof? Well, we'll never know, but Andrew Wiles did. In fact, the proof itself is over 150 pages long and consumed 7 years of Wiles' research. For solving Fermat's last theorem, he was knighted and received other honors. But everything was fine until Homer Simpson stepped into the fray. Homer actually wrote an equation during an episode of The Simpsons called The Wizard of Evergreen Terrace. Homer appears to write a valid solution to defeat Fermat's last theorem. Look at the equation above and then compare it to Desmos. Desmos took the first two sums and compared it to what it equaled, and it's a hit. It's the same. They're the same. So he found something that disproved Fermat's last theorem. Well, almost. The devil is in longer approximations. In the 10th place, it fails. And we need exactitude to prove the theorem. So the 10th place, you notice, are different. Andrew Wiles has nothing to worry about from Homer Simpson. Simon Singe wrote a book about that, and it's a great read, very worth getting that book. By the way, Simon called Homer's attempt at a solution a near miss, which is not a proof. Speaking of long approximations, how accurate is Google? Take a 19-digit number and subtract it from one more than the 19-digit number. You should get an answer of -1, right? Well, wrong, because Google said 0. And Google actually blows it. Why? It has the same problem that Homer had. It has to do with limitations that calculators have in computing large numbers. So it's a computation problem that caused this. My next story has to do with something called The Weird Number. It's a movie, a 12.5-minute video, and it has to do with a story that occurs in a town only inhabited by natural numbers. Here's the opening scene from The Weird Number.
My story concerns a strange event that took place in a little town nestled in the mountains. A little town inhabited only by natural numbers. But whenever the townspeople gathered together, rumors were exchanged, rumors that other numbers lived in the dark woods beyond the mountains. But no one could imagine a number that wasn't a natural number, so no one believed the rumor. At that time, nobody worried about robberies because if, for example, 5 stole something, he would always take 5 of whatever he stole. There was no special reason. That was just how he did things. And 7 would steal 7 things, and 10 would steal 10 things, no more, no fewer. And because of this, the thief could be easily identified. So there weren't any robberies, and no one bothered to lock things up. But one day, there was a robbery. 9, who was the baker, rushed over to the sheriff's office. 763, who was the sheriff, leaned back in his chair and asked 9 what was stolen.
Just a little piece of bread.
1 piece of bread, said 763. I can't believe it. 1 is the mayor. He would never steal.
No, said 9. Not 1 piece of bread.
A little piece of bread. Not 1 piece of bread, but a piece, said 763. What kind of nonsense is that? I'll show you, said 9. Then you'll understand.
The baker proceeds to explain to the sheriff that a little piece of bread was stolen, so it couldn't be a natural number. So if not, so who was the culprit? It was 2/3. So the sheriff got a posse together, and they thought they had him cornered in the barn, but when the door was open, it was 4/6, who then explained to the posse that he didn't know where 2/3 was. So the posse continued to search for 2/3. In the meantime, fractions joined the natural numbers in town. Now I'm going to show you the last minute of the video. If you want to see the whole 12.5-minute video, there's a link at the end of the presentation. So here.
Throughout the years, many of the rational numbers from the woods came into the town to join the natural numbers, until the time came when all of them lived there. Even 2/3 came, and 763 continued to chase him. But 2/3 always found a new form to escape from 763. Many years later, rumors came that strange new creatures were now living in the dark woods beyond the mountains. The rumors said that these creatures were numbers too, but they couldn't take the form of a natural number on top and a natural number on the bottom. It was said that some of these numbers were rational numbers, but some weren't. But no one could imagine what a number would be like that couldn't take the form of a natural number over a natural number. So no one paid any attention to the rumor.
I always hoped there would be a sequel to the weird number, but as far as I know, one was never made. So what were these strange new numbers? One way to describe them is they are numbers you can't count on. Which takes me to the story number 5, where I will introduce you. That's right, the irrationals. Here's a famous square root of 2 is a famous number, 1.414. The digits go on without a pattern. Also, you can't get an exact measurement for the square root of 2. The diagonal of the square, which is equal to the square root of 2, is incommensurate with measurement. One of the Pythagoras' followers discovered this and revealed this mathematical secret to the world and suffered the consequences. It's a stormy day on the sea off the coast of Greece. The date is around 520 BC. Fighting for his life, a man is heaved over the side of a boat and dropped into the open water to die. His name is Apasus of Metatopen. His crime, telling the world the mathematical secret, the secret of the non-rational number. I got my idea from this book, The Irrationals by Julian Havel. However, it's very detailed and probably it's not appropriate for the lay reader. but a Cliff Notes version would certainly be helpful. So let me take you to story number 6, Desmos and green globs. You're probably familiar with Desmos, but not green globs. The folks at Desmos caught wind of green globs and turned it into a Desmos version. Well, sort of. It was left bare bones since it couldn't quite capture the essence and motivation of green globs. Notice here that if the function hits one of the globs, then you get 1 point. If it hits a second glob, as it does in this particular function, you get 2 points for the second glob. Third glob gives you 4 points, and the fourth glob gives you 8 points for a total of 15. So that would be the score you would get. And the object, then you would repeat the process with a different set of globs and a different function. Here's the green globs version. You're about to see the relation below get graphed. Here goes. You'll notice that as the function flows, it hits the globs and it makes a exploding sound. And it hits 6 of them. So you get a total of 63 points, which is the same as 2 to the 6th minus 1. Also, the score gets registered in the upper left-hand corner. Green globs is challenging and addictive. This leads me to telling you my final story. Guillermo's big score. It's amazing what globs can do for a bored, disinterested student. This is Guillermo, who was upset because he was not accepted into the 8th grade advanced class. After being introduced to globs by me, he was intrigued and began playing it regularly. He would also sneak into the advanced class, which he wasn't a part of, where he learned some fancy tricks to down more globs with one function or equation. For example, this is a report Guillermo wrote, and this was one of the challenges he took on. And this is the advanced game. If you play the advanced game, there are these circular blockers. So what prevents you from doing a sine function with that would cover the whole grid, the blockers would stop that and you get no score if you hit a blocker. So you had to somehow manage to get those globs without hitting a blocker. Here's one. He did an absolute value function and got 2,050 points because he was able to get the V-shaped of an absolute value function with a long sine curves, following the producing a sine curve that misses the globs, misses the blockers, I mean, and he got a high score. One day, Guillermo's teacher gave me a call to let me know about what Guillermo accomplished with the challenge above. He came up with a sine function that made a wavy curve along the linear path defined by the linear part of the function. He got them all. Here's what Guillermo wanted to show me. Again, there are 13 globs and 5 blockers. Watch what happens. He got 2 to the 13th minus 1, 8,191 points, which is obviously the most points you can get. Because of the strong interest in globs in my classes, I held great green glob contests, which were very popular. They kind of stopped when I retired, but certainly love to see them start up again somewhere. So that's it for me for now. You've gotten a glimpse of a few vignettes that inform what I call Math 2.0. I'll have more for you in the future. Actually, the future is now. So let me share some more examples of Math 2.0 stories that I'm working on. The famous Jinx puzzle, birthday problem, bridge around the earth problem, 13 times 7 equals 28. Yes, it really does, sometimes. Measure the circumference of the earth, Pick's theorem, Curry's paradox, paper pool, and all of these will come in a package called the SeasMath Activities 2.0, which you can take a glimpse at some of these now. Yes, here's the references for this little presentation that I made for you. If you click on, for example, the intro to globs is fun because you really get to see why globs is so addictive to kids. And others, and there's the SeasMath link, which can take you to SeasMath activities that I currently have posted, and I'm working on future ones. So I guess all I want to say now is thank you for watching, and I look forward to connecting with you sometime in the future.